Laplace transforms. This is going to be a marathon. We have 1, 2, 3, 4, 5, 6 questions, which isn't too bad, but they're pretty long and involved, all of them. Um, Not so much of a marathon as the Laplace initial value problems thing that I have to record tonight as well. So it's Laplace season around here. This is including every single Laplace question that we get on the final, so it's not discriminating based on the kind of stuff you're likely to see on midterm two. I learned them kind of all at the same time. Really, reading off this sheet is not a skill that takes a couple weeks to build up. So it's not so bad. But just so you know, if you're seeing stuff on here that you haven't done before and you're doing this for exam two, likely you're good. Yeah, you should probably are only worrying about um, the sine, cosine, maybe 9 and 10 as well, and number 2 and 1. But in general, like we'll be running into to 16 and 17 along the way, and a lot of 13, but it's probably not stuff you have to worry about. Keep that in mind. Um, but there we go. That's the long disclaimer for this one. Let's get into it. Let's find the Laplace transform of this piecewise function here. So whenever we see something that's piecewise, we know that we need to use unit step functions. So those are in the form uc of t, where for all values of t less than c, this thing evaluates to 0. For all values of t greater than or equal to c, it evaluates to 1. So for t between 0 and 1, we want our function to evaluate to t, and we can set that up in a little bit of a convoluted way, but with 1 minus u1 of t times t. So as long as t is not greater than 1, this whole bit will evaluate to 1, so we'll get our t. But the minute that t is greater than 1, this will be 1, so this evaluates to 0, and there's a plane flying overhead, and the whole thing will evaluate to 0, and all we need to add on top of that is plus u1 of t, just so that once we hit that value of 1, that the function picks right back up as just being equal to 1. So if this is f of t, let's do some rearranging things to see if we can put this into a little bit of a nicer form. We have t minus t times u1 of t plus u1 of t. Let's factor our u1 of t out. We have t minus u1 of t, and then this will be t minus 1 in here, and this is still f of t. And now, actually, everything is in a form where we can take our Laplace transform pretty easily. The Laplace transform of t to the n is n factorial over s to the n plus 1. The disclaimer I say every time I use alpha, I like writing it, and my s's look like 5s. So our Laplace transform of f of t will give us 1 over alpha squared, because we add 1 to the power here, and we'll get s squared in that denominator. And then we are subtracting u1 of t, where in this case c is equal to 1, and then some function where all of our t's are replaced with t minus 1s. This is exactly what we are looking for here. So that Laplace transform gives us e to the negative 1s, in our case alpha, multiplied by the Laplace transform of this function without the minus c in it. And that just gives us alpha squared. So this is 1 minus e to the negative alpha over alpha squared. And that is B. 17, let's find the Laplace transform of this unit step function related piecewise thing that we got going on here. So when t is less than pi, we want everything to evaluate to 0. When t is between pi and 2 pi, we want t minus 2 pi. We're already seeing that kind of t minus some constant c, and we know we're going to have unit step functions with 2 pi in them. So that's something to be thinking about. So how can we set this one up? Well, if we have 1 minus u pi of t multiplied by t minus 2 pi, what will that do? So when t is less than pi, this will evaluate, nope, sorry, did that slightly wrong. This will evaluate to 0. When t is greater than pi, this will evaluate to t minus 2 pi. So now we can subtract from it u 2 pi multiplied by t minus 2 pi. So now that we have our function figured out, our f of t, we need to do a little bit of shifting things around to get everything in the form that we like. This is already good. We have uc of t, I forgot the of t in here, and then multiplied by some function of t where all the t's are replaced with t minus 2 pi's. But over here we're not so happy because we have u of pi and then t minus 2 pi. So all we can do to fix that is say that f of t is equal to u pi of t times t minus pi. And now what's happened here? We should have a negative pi u pi of t outside, because we could factor that back in and we'd have a negative 2 pi. And then we also have our negative u of 2 pi, u pi of t, u of 2 pi of t multiplied by t minus 2 pi. And everything is looking good now. We can use the fact, okay, I'll be clear here. We're taking the Laplace transform of f of t. And let's just go left or right. I won't kind of jump ahead. So we have uc of t multiplied by f of t minus c, and that will just become e to the negative pi alpha multiplied by the Laplace transform of this thing with no negative pi's in it. So that's just 1 over alpha squared. And then our negative pi u pi of t will just become minus pi e to the negative pi alpha over alpha, because this negative pi constant can just stay outside of the Laplace transform, just like we can pull factors out of integrals and get away with it. So that, yeah, that I'm just making sure that we've got that. Okay, that looks good. And then finally, this last guy will give us minus e to the negative 2 pi alpha, all divided by alpha squared. And that leads us to which one of these? Having a hard time reading tonight. I need to check through this. E to the negative pi alpha over alpha squared minus pi over alpha e to the, yep, and then, yep, okay, just making sure we're good there. 14, we're finding the Laplace transform of this function. So for t between 0 and 2, we want our function to be equal to t. So let's have f of t, I'm bad at spacing this, f of t is equal to, well, just t, and then we can have minus u2 of t, and then t minus 2 in there. Isn't that so nice how that works out? Because when t is greater than 2, this will evaluate to 1, so we will have t minus t plus 2. So that gets rid of this, adds that 2 in there, and we are good to go. And this is very easy very easy Laplace transform at this point, because the Laplace transform of f of t, we don't need to do anything else to get it into a form where we can take our Laplace transforms of these bits. This is 1 over alpha squared, and then minus e to the negative 2 alpha, all divided by alpha squared, because remember, our, where'd it go? Our big F of s term is just the Laplace transform of the function f of t. And remember, over here we're dealing with t minus c, so we have to remove that negative c and take our Laplace transform normally. So we're just Laplace transforming t, which is 1 over alpha squared. And so that is giving us 1 minus e to the negative 2s over s squared. Laplace transforms, they're still happening, except this one isn't so bad, although we have a little bit of a case of nested computations to deal with here. So whenever we take the Laplace transform of some function multiplied by e to the t, here we go, e to the ct times some function of t, that's just the Laplace transform of f of t, but we replace all of our s's with s minus c's. So all we have to remember, at the end, alpha equals alpha minus 1. We have to do that replacement operation. And already we see in here, there's some alpha minus 1s. That's a good hint that that might be a good answer choice for us. But either way, we're using rule 16. Otherwise, we're going to ignore this e to the t for now. We have the integral from 0 to t, check, of f of t minus tau. That's our cosine of t minus tau. So f of t is cosine of t, and g of t is just our g of tau term in here, so that's sine of tau, so g of t is sine of t. And this gives us the product of the individual Laplace transforms of both of these. The Laplace transform of f of t will give us alpha over alpha squared plus 1, and the Laplace transform of, gotta keep the same pattern here, g of t will give us 1 over alpha squared plus 1. So in all, taking the product of their two Laplace transforms, we get alpha over alpha squared plus 1 quantity squared. And all we're doing, at the end, we have our little asterisk up here. We have to replace all of our alphas with alpha minus 1s. So that's alpha minus 1 over alpha minus 1 squared plus 1. And what do you know? Our scouting the answer choices early paid off. 17, another Laplace transform of something that is in this same form. I didn't really try to order it this way, but it worked out. So we see that I'll do f first. F of t, which is everything with a t minus tau in here, will just be sine pi t, and g of t is just everything with only a tau. That will be t squared e to the negative t. And we know that this Laplace transform is just the individual Laplace transforms of both of these multiplied together. So capital F of alpha is just the Laplace transform of sine of pi t. That's pi divided by alpha squared plus pi squared. And then capital G of not t, but alpha, because we're in the Laplace alpha domain or S domain, whatever people call it. And then we're going to be using t to the n times e a to the t, where n is a positive integer. That's true. N is equal to 2 in this case. We get n factorial, so 2 all divided by alpha minus the a value here, where a is negative 1, so we'll have plus 1, to the n plus 1. So that's to the third power. And now we're just taking the product of these, and I'm just going to choose the answer that works. We have 2 pi on top, and then all this extra stuff on the bottom. Let's find the Laplace transform of this function. They really do like making us use this formula because most everything else, like 17 and more of the unit step function stuff, shows up with the initial value problems, which I'm going to go force myself through after this. So our function f of t is t cubed up here because that's the only thing that doesn't have a t minus tau replacing all of its t's or taus. And then g of t is everything in here that has t minus tau, just replacing those t minus taus with t's. That's e to the t cosine of t. And blah, blah, blah. We know the drill. We got to find these Laplace transforms. The Laplace transform of f of t is f of alpha. That will be n factorial, so 3 times 2 times 1, 6, all divided by, and I'll go show you the formula, there it is, all divided by, s to the n plus 1, so alpha to the 4th. And then capital G of alpha is just going to come from e to the at cosine bt, where both a and b are equal to 1 in this case. That gives us alpha minus 1 divided by alpha minus 1 squared plus 1. We can expand this to be alpha squared minus 2 alpha plus 2, alpha squared minus 2 alpha plus 2, and then our final result is just these multiplied together, just like rule 16 tells us to do. And so that will give us, believe that right there. And this is wrong because we need a negative 2s. There we go. And that's it. This was way more painless for me than I expected it to be, which is, I guess, a good indication because my midterm 2 opens up tonight at midnight, and I'm debating taking it then. Either way, wish me luck, and I wish you luck on your upcoming exam.